Let's talk about a common problem in classical mechanics, the projectile motion problem. For projectile motion, if you are working on a problem or have seen one in the past, you might have noticed some things that are common amongst these style of problems. You are usually given some location of a launch, whether that is a mechanical launching device or your launching device is a person to throw a ball or a rock into the air. And then there's a drawing that's a parabola that traces the motion or the trajectory of where that projectile goes, and it either comes back to rest on the ground or on some elevated position or some de-elevated position. In this case, specific to the problem we're going to look at, you can think of some launching mechanism launching a projectile onto the top of a building. Now, there are initial things that are given to us, measurements that are taken on the motion of the projectile that help us solve our problem. In our case, we know the time. So here are our given elements. We know the time. So somebody pressed the launching mechanism, the projectile launches into the air, and at that moment somebody hits the button on their stopwatch and watches it until it comes to rest, and then they stop it. You know the time. No surprises there. Another thing that we know is the height, h, at which it lands relative to its height when it launched. So we have h. We know the height of the building. Now, often there are other initial measurements that are taken and given to help solve the problem. For us, what we want to know is d, the distance in the x direction, or the horizontal distance traveled from launch to landing of this projectile. So we don't know d. Oftentimes you'll see a problem given where the initial velocity is known, so the magnitude of the velocity and also its initial angle relative to the horizontal. In our case, we do not have those. We do not have the initial, we do not have theta initial. We do not have the luxury of having these in our arsenal to solve this problem. So then, if this were all that was given, this would be an unsolvable problem. We're going to look at this in a sort of unique perspective to show something that is in itself unique about classical mechanics. What if we were given the final theta, so theta f, the angle relative to the horizontal of the top of the building of the landing trajectory, the trajectory of motion of where the projectile lands? You can imagine somebody having been gone up on top of the building before the projectile was launched, and they have a bit of a mechanism, whether it looked like a sextant or something like that, to measure the angle which it lands. Now, that is maybe a lesser familiar type of problem, to be given a lot of bits of information, but then to be given information about its landing position rather than its launch trajectory is not as common, but it helps to illustrate a really interesting point about classical mechanics problems. So we're going to go with it. We're going to see, can we solve for d if we're given the height, if we're given the time, and if we're given the final theta final. All right, so these are what are given, and we want to solve for d. This is what we need. Okay, projectile motions of equation, x equals x naught plus the time times the x component of velocity, and then the y projectile motion equation, y naught, plus the time times the y component of velocity. Now these are initial velocities. And then minus 1/2 gt squared. So this term, this last term in the y equation, is the effect of gravity. It's the gravitational field strength, g, times the square of the time divided by 2. So common enough equations. They shouldn't be too unfamiliar, hopefully. Now, how are we going to do this? Because as I just mentioned, these are initial velocities, which we do not have. And even if we did have initial velocity right here, we would need to find its components by having the theta initial, which we don't have. How is this actually going to be a solvable system? Well, here's the uniqueness. In classical mechanics, the laws of physics work identically forward as they do in the reverse direction. So if you're given a problem like this, you could say, what happens if instead of looking at the problem from this perspective, if I mirror it in my head and look at it from the other direction, such that our coordinate system begins here, here's the origin, and x runs to the left, and call this the launch position. Think of the motion as being launched from on top of the building and landing on the ground. Could it work? It does, in fact, work. In classical mechanics, physics works in the forward direction identical to the reverse direction. This is in contrast to other branches of physics or more complete theories of physics, such as adding relativity or something like that, where this would no longer be the case. But in our everyday lives, the laws that govern motion are very well described by this type of idea. Okay, so this is exactly what we're going to do. We're going to, in our minds, flip the picture around, start from here, launching from on top of the building, landing on the ground, see if we can get to solve for D. All right, so using our two equations of motion, we have x. Now, x is the total lateral distance traveled by the projectile, which is d. So x becomes d. Now, x naught, this is the initial, x naught and y naught are the initial biases of position relative to your coordinate system. Now, I had the freedom of drawing my coordinate system wherever I wanted. So x naught and y naught become 0. So there is no initial x bias in that direction. We simply then have t and v naught in the x direction. Good. Now let's think about y. Now y is the final, the overall amount distance traveled in the y direction throughout its flight relative to where it began. That will be h. So relative to where it began on top of the building, it will come to rest on the ground, and the difference in position is h. We write it as negative h because relative to y at the origin, it travels down in the negative direction, a value of h. Okay, so that takes care of y. What about y naught? Well, y naught is also equal to 0 because of where we've placed our origin. So it goes away. We then have t times initial velocity in the y direction, and then all of the components of this term we know. T is given to us, it's something that's measured. G is a constant, at least on the surface of the Earth, and this is how that equation will look. Perfect. Okay, now where do we go from here? We have two equations, and as it's written, we have three unknowns. Now that's a no-go for solving systems of equations. Systems of equations demand that we have as many equations, independent equations describing our motion or our system as there are number of variables or number of unknowns. So we've written Vx, Vy, and D, three things we do not know, but we only have two equations. Well, there is a way to get around this, and that is to rewrite these velocities. We don't have V naught. Now, in the manner in which we are looking at this problem in the reverse direction in time, we could call this our V naught or V launch, the initial velocity. We don't have it. Nobody was there with enough stopwatches or stop motion cameras or anything like that to try and measure it. And so it's simply an unknown. That doesn't bother us though. If we could rewrite these in terms of a single variable v naught, then it would allow our system of equations to become solvable. So we do know theta f. Therefore, we can write Vx as equal to v naught cos theta f. And we can write Vy trigonometrically as v naught times sine theta f. We know theta f, therefore, if we substitute these expressions into our equations, we will have two equations with only two unknowns. I can rewrite this as t v naught cos theta f. Then I'm going to expand this a little bit for space. This will be v naught sine theta f minus 1/2 gt squared. All right, now we're getting somewhere. Two equations, two unknowns, a solvable set. Solvable is what we want. It's what we like. Okay, now, it's usually up to a person's preference of how they proceed with a system of equations, which one to rearrange first and then insert into the next. I'm going to take a simplest first approach where I regard this first equation as the simplest. It has the least amount of terms. I'm going to solve it, or rearrange it, so to speak, for v naught, and then I'm going to substitute that expression into here for this v naught. That will leave d in the equation, which I can then ultimately solve for, which is what I want. Okay, so if I rearrange this, I get that v naught is equal to d over t cos theta f. That's good. Now I'm going to take this expression and replace v naught with it in this second equation. All right. So let's see. D over t cos theta f. I'm going to have minus h equals t d over t. And I will have sine theta f over cos theta f. All right, so the d, the t, and the cosine theta were from the x equation, solved for v naught. And then the last term remains the same. And here, now, is something we've been looking for. A single equation, a single unknown. Let's solve it for d. Notice that the t's cancel. Sine theta over cosine theta is tangent. So we have the simplified version. Negative h equals d tangent theta f minus 1/2 gt squared. And I'm going to rearrange that and finally come to our answer, which is 1/2 gt squared minus h over tangent theta f. All right. Not bad. My handwriting wasn't the best there. Hopefully that's readable. So the main conclusion here is not that we've solved really this particular projectile motion problem. It's the method for solving a problem of projectile motion is common. They're all somewhat similar. There's similar elements. There's only a finite list of information that is necessary to solve them or that will be given initially. What's unique about this and what I would like for there to be taken away from this is that if you ever encounter a problem in classical mechanics, whether it's projectile motion or otherwise, if you are asked to solve for something and you're not given initial conditions that you are familiar with, think and ask yourself, are there enough final conditions? If there are enough final conditions that I'm given, perhaps I can, in my mind, mirror time, look at the problem in reverse, knowing that for classical mechanics, physics works the same both ways, and then solve for whatever it is you're asked to solve. All right, that's it for now. The very best of luck.